Okay, great. So I'm Kwang Ma from UC Davis. So it's my great honor to introduce today's keynote speaker, Professor Remco Chang. So Professor Chang studied at Johns Hopkins and then Brown University, and finally he received his PhD from North Carolina, UNC, University of North Carolina at Charlotte in 2009. Yeah, yeah. And, so before he joined the faculty of Tufts University, he actually spent a couple of years at the Boeing company. Yeah. Actually, I didn't know that you work at Boeing. Yeah. So Professor Zhang has been actively serving our research community. For example, he previously served as the program chair for VIS 2018. And most recently, he served as the general chair of VIS 2024. Currently, he's serving as the associate editor for two of our best journal. One is the ACM Interactive Intelligence System, and the other one is IEEE TVCG. So Professor Zhang's research, as most of you know, is very outstanding. He has received various recognition. For example, he received this very prestigious award, U.S. National Science Foundation Career Award, and also his team has received multiple Best Paper Award. And also, very amazing that he's a co-founder of 2 startups. Yeah, very great. And so his research is more in visual analytics, I would say. And so today he will share with us his framing a foundation for visual analytics. So let's welcome Professor Zhang.
Thank you, Kwang Lu, for that very generous introduction. I want to thank the organizers of PacificVis for inviting me here. So I was born in Taiwan. I grew up here until I was 12 or 13. So it's a great honor to be here, especially because my mom is here. So mom gets to see me the keynotes. All right, so yeah, I wanted to share with you some of the work that we're doing recently towards the theoretical part of visual analytics. So the title of this talk is called Visualization is Worth 1,000 Queries towards a Foundation for Reasoning in Visual Analytics. So to start with, I want to recognize the pioneers of the visual analytics community. We have Jim Thomas, Chris Cook, Bill Rybarski, who's my advisor, Alan McCachran, we have David Ebert, Pat Henrahan, and John Stasko. And in about 2004, 2005, they wrote the book Illuminating the Path, which served as the research agenda for the community. In 2006, at the VAST conference, or the first VAST symposium was held. So I know that Ross later on is going to give another keynote talking about a sort of reflection of the community. So this is just going to be a short one in terms of what I think that we got right and things that we didn't go quite as planned. So first of all, I think the community got right that this notion of human plus AI machine learning is indeed sort of the right way to deal with large, complex, dynamic data. So kudos to us. And the second thing we got right was the Tableau company, which, you can say came from this community. Sure, whatever, we'll take credit. So obviously, it's one of the most successful stories out of the Viz community. The company was sold for $15.7 billion. And then, of course, we've had a slew of systems, applications, and tools. Those are great. Things that we didn't plan out to go as they did. So unfortunately, after nearly 20 years of this, we still get this weird question about what is visual analytics. Is it just applied visualization? Is it about just lots of coordinated multiple views? Is it sort of super complicated systems for experts, or is it just an interface slapped on top of machine learning and algorithms? And here I use one of my systems from the past just to illustrate that these systems, after 20 years, still look quite complicated. And more specifically for this talk, I think, right, I've been reflecting on this a lot, which is that unfortunately as a community, we never actually had a chance to develop its own foundational theory. So because we don't have this foundational theory, we can't really even talk about what is visual analytics, what are some operationalizable foundations. And for me, one of the sort of thing that irks me is I look at every professor who teaches visual analytics around the whole world, and everybody's curriculum is a little bit different. So we don't actually have an idea about how to standardize the core topics in the visual analytics core. So if you think about this epistemologically speaking, so we have the SciVis community who draws from computer graphics and physical sciences. So there's a pretty solid foundation there. InfoVis draws from HCI, perceptual science, and from design principles. And there's also a pretty solid foundation there. And for us, we're supposed to draw from data science, including machine learning, AI, databases, and so on, and cognitive science. And we're sort of not quite there. And building on the work of these pioneers, I advocate this idea that we need our community to develop its intellectual core. So, first, I hope that you guys would join us in thinking about it. All right, before I sort of give into my spiel about how I think about one way forward in building this foundation, I want to give a little background in terms of how I think about VA systems. So here's a very simple example. Imagine I just have a simple scatter plot, and the user wants to select some points by drawing this bounding box. So the way we do this in JavaScript or C++ will be something pretty procedural, like you have a for loop that loops over the data points, and then if the data points values or parameters are within the bounded area, then let's say you print the name and the age and so on. But we can think about this exact query in a different way, or this exact process a different way, thinking about it from a SQL query standpoint. Now the SQL query representation of that same operation now is a lot cleaner. So I do select name and age from data, and I have a where clause that defines essentially the same bounding box. So the argument here, of course, is that instead of writing this for loop, which is complicated, confusing, now I have a more concise and more semantically meaningful representation. So this idea is not new. So in 1992, Ben Schneiderman wrote the dynamic home finder, which looks something like this. So in this visualization, the left-hand side is a map, and the right-hand side is a bunch of sliders and widgets. And the idea is that user can use these sliders and widgets to filter out the homes that they're looking for. And if you look at it in terms of a SQL representation, it's also really simple. You just select the latitude and longitude of each home from the homes table with these criteria as the user specified. And what this means is that you can rethink about Home Finder as a parameterized SQL query where the parameters of this query are directly bound to the UI elements, right? So the distance is greater than slider 1 min and max, then the price is between slider 2 min and max, and so on. So Ben Schneiderman figured out this connection between interactive visualization directly to SQL queries, in particular as parameterized query. So as it turns out, many visual analytics systems are essentially just wrappers exactly the same way that Home Finder was. So here's a bunch of examples of systems that I've found, and I wrote some of these, so I know, right? So these interfaces might look really fancy, but under the hood, they're just parameterized SQL queries. They're nothing really special, but the interface looks really fancy. As a side note, I think that this is a very potentially interesting way for us to think about sort of the nature of these systems, whether or not they are just in fact SQL queries kind of wrapped around. Okay, so with that motivation and background, the talk overview here is that I want to suggest that the use of queries, languages, and grammars may be a promising path towards developing an operationalizable theoretical foundation for the community. So the talk is going to have 3 parts. I'm going to give you a motivating example and 2 just very sort of theoretical way of thinking about things. Yeah, I hope you drink your coffee because the stuff is really abstract, so you have to bear with me. All right, the first one, the motivating example, this is work done with the folks in Arizona. Some of these are, yeah, you know a lot of these people. The idea about the system neurocubes is about approximating a database using a neural network. So here's an example. Let's go back to the home finder. And the idea is that if we're giving a set of values for parameters P1 to P6, I modified the original query a little bit. Now, instead of selecting lat long, I'm selecting the average price, number of bedrooms, and then the whole query is grouped by bedrooms. So if you're given the values P1 to P6, you can run this query, and you get back a table like this. Right? So you have the number of bedrooms on one column and then the average price on the other. And the way that the InfoVis pipeline works is you would take that table and then you'll sort of put that into your standard visualization, and where you get this bar chart. So I wanted to simplify this a little bit by, first of all, thinking about not just the whole query, but just treat it as a parameterized function, f, with the 6 parameters P1 to P6. And then for the table that's returned, I'm just dropping the header, so I'm just only keeping values here. I'm further going to simplify this by just showing the results as just some vector of values v1 to v4. And just for simplicity, I'm going to drop the visualization for now, because we know how that works. Rewrite this a little bit, and now moving things. So the question that we have is, we have P1 to P6 as your inputs, we have V1 to V4 as your output. And the question about the NeuroCube paper was, can we learn the relationship between the two? Right? So can we learn the relationship between the input and output spaces? More specifically, we want to learn a function f as a neural network with input of P1 to P6 and output of V1 to V4. So how do we train this neural network? So we have P1 to P6, and the way we're going to do this is just randomly pick values. So randomize each of those values. And once we have the values of P1 to P6, we can throw it back into our parameterized SQL query. And then that gets executed on the database. The database is going to give us the value of V1 to V4. And then we'll use the input and output to jointly train this neural network. So the big picture idea is this. So typically, the way we think about the InfoVis pipeline is that we have a database, ask it some query, get back some values, use those values to render your visualization, right? So this is pretty standard. Now, what we're doing a little bit differently is, while this is happening, we're simultaneously using that information to train the neural network. And the trick is, once the neural network is trained, then we just throw away the database. So now instead, the visualization is directly querying the neural network, not the database anymore. And we can use that neural network as a surrogate to the database, and then we use that to drive our visualization. So if you look at this visualization, it's your standard geospatial temporal visualization. It feels sort of fully featured. You have a map that you can pan and zoom, have some timeline charts that you get to filter by months, days of the weeks, hours of the day, and so on. In this particular case, which is showing the Bright Kite dataset, which is a location dataset of when people use their social media applications. Okay, so some sample results. Now this is sort of, this work was done in 2020, 21 or so. So it's a few years old, but nonetheless, the results pretty impressive. So if you look at the blue line, these are the results of the visualization if you query the database directly. And the red line is our approximation of. So this is, the red line is shown where the visualization only gets to query the neural network, but not the database. And obviously the takeaway here is that the two results are extremely similar. So showing that the neural network really was able to learn the database results. So what does this matter? Well, so there's just some sort of experimental results. When the data set is pretty small, the original data is small, you don't save a lot. But obviously, when the data set gets bigger, the saving can become a little more significant. And more interestingly, here's an example, right? So the interesting thing here to note is that when the raw data size goes up, so when we started training with only 1,200,000 rows, and going all the way up to training with 12 million rows, what happens is that we now have actually more training data, and the result of this is that our error rate actually starts to go down. So this is sort of pretty intuitive if you think about it. The neural network gets better if you have more training data. That's not very surprising. But we get sort of the double benefit of this. Not only does the training go down, in this particular case, our model size, essentially the neural network stays exactly the same. So in that sense, when at the extrema case, the space saving is almost 2000x, right? So instead of a database of 1.8 gigabytes of data, we could represent that entire database with just 800 kilobytes. So 1 megabyte is all we really need to represent. So there's some sort of high-level thoughts out of this. One is just this really sort of existential question about this result. So what I mean is that typically when we think about visualizing and interacting with a very large database, let's say 1.8 gigabytes, we think about interacting with a lot of data. But what's interesting here is that we can now approximate that with far less information in the scale of 1 megabyte. So there's a real sort of interesting philosophical question about what is the user really seeing when they're interacting with a very large data set. And related to that, in this reduction, what information is being thrown out? So I don't have an answer to this, but Min Chen has been thinking about this for a long time. So I refer to you to some of his work. And I'm happy to chat more about this sort of philosophical point some other time. But for the purpose of this talk, I just want to mention that this technique works really well. And the takeaway here is that if we consider a VA system as just a parameterized query or function, we now have the means to think about this more structurally, and we now have the formalism to reason about what the system is doing, which leads to opportunities for optimization. Okay, so with that backdrop, I move towards thinking about this notion of using queries to model visual analytics systems. So the idea about thinking about visualizations as languages, grammars, queries, and so on is obviously not new. There's been a lot of languages and grammars, very successful ones in the Viz community. We have, starting with Wilkinson's Grammar of Graphics, we have D3 Vega Lite, Matplotlib, we have VizQL for Tableau's internal query language, and then we have a whole bunch more. So these are all great, but sort of my view about all these grammars and languages is that these are all really designed for expressivity. So in other words, they're meant to be for programmers to use to program visualizations, but they're not actually as good for the purpose of representation and reasoning. And here's what I mean. So I think about the InfoVis reference model. This is the Stuttgart model from 1980 something or other. And the idea behind the InfoVis reference model is pretty simple. It just says you start with some source data, you do some data transformation, you get the data table, and then you do your visual mapping to get your visual abstractions, and then finally you have your view transformations to create the view that you're seeing. So almost all of these Viz authoring libraries take the same approach. So they follow the InfoVis reference model. This is great because it allows for convenient visualization, recommendation, and validation based on data type matching. So in particular, McKinley's APT. So just as an example, let's say I have a two-dimensional data set, categorical versus quantitative. Using the InfoVis reference model, we can say that we can visualize this 2D data set using a bar chart, a pie chart, a scatter plot. So here's an example of doing this in Vega Lite. The scatter plot is written as mark is a point, and X maps to A, Y maps to B. And if you want to change that very quickly to a pie chart, all you have to change is the mark from the point to an arc. X goes to color, Y goes to theta. You just change a very few, or you just have to change a few words. All of a sudden, instead of getting a scatter plot, you get back a pie chart, right? So that's great. So from an authoring standpoint, this is fantastic. So here's some examples of visualizations, those bivariate visualizations I just mentioned earlier, and their Vega light specifications. So if you look at this, one of the first things that should jump out at you is that the scatter plot and the pie chart should look very similar. So they just have the mark and then the X and Y map to attribute 1 and 2. And the bar chart looks a little bit like a modified version of a scatter plot because you have this additional aggregation function over the attribute 2 field. And then the proportional stack bar chart is the really complicated one. It's sort of a bar chart, but it has all these voodoo magic that has to happen. So in this sense, this guy seems very different, and the others look sort of more similar. The whole idea behind this work is to say, whoa, hold on 1 second, right? If we expose what's happening under the hood, and this is what we call design-specific transformations, things start to paint a slightly different picture. So what we mean by design-specific transformations is the idea that before you can render your bar chart, the fact is you have to do some more operations on top of your data. So in particular, to render the bar chart, you need to do this group by, right? To take all your data points, group by the categories. And in this case, you're doing a sum. You're summing over each of the attributes. And for the pie chart, you're doing sort of exactly the same thing, but you have to do more work because instead of showing the sum, you want to show the percentages. You have to compute the total and then divide each of those group by results by the total. And one more thing, you have to actually compute the offset. So you have to know exactly where the mark is placed by knowing what the offsets are. So the funny thing is, if you look at the pie chart and the proportional stack bar chart, all of a sudden you realize that their data transformations are exactly the same, whereas the scatter plot be further apart. So if you look at the example results of running these design-specific transformations, it kind of looks like this. So the scatter plot has no transformations. It's literally just mapping X, Y to the 2 fields. So you just have your raw data. In the case of a bar chart, this is what actually gets rendered, right? It's a table of the group by results and the sum. And the pie chart and the proportional stack bar chart are rendering the same things. But it's no longer the raw data. It's now these percentages and offsets. And so on. So after you compute all this stuff, then what happens in the visual encoding step is not the raw data again, but you're doing the visual encoding over what we call the prepared data, essentially the results of the design-specific transformation. So altogether, right, now you start to see a slightly different picture about what's actually happening in each of these visualizations. So what can we do with this idea? Well, the first thing that we realize is that, right, in the Viz community, we've had this question about pie charts being really good at showing parse-the-whole relationships. And that's one of the arguments of why you use pie charts and not bar charts. So the question is, why are pie charts actually better at showing parse-the-whole relationships than bar charts? So currently, the way we teach students is that you just memorize this. This is a design philosophy. Tell students that parse-the-whole relationship, show a pie chart, otherwise always use a bar chart. So why is it actually better? Well, it turns out that, right, so as an example of this, right, so what is the percentage of C1 in the whole data set? Now, the argument is that the pie chart is a good visualization for this task because effectively the design-specific transformation already pre-computed that percentage information. All it's doing is just literally drawing that information as an angle. So on the other hand, when you have a bar chart, I think it's a bad visualization for this task because as a user, you have to mentally compute the sum of these 3 things and then have C1 divide over the sum. So in that sense, there's all these mental arithmetic the user has to do. Second observation, so is it valid to compare bar charts with pie charts? So typically we think yes, right? They sort of encode the same amount of information, but the argument here is not really, because I argue that they're different visualizations because they actually encode different types of data. So again, the pie chart is actually visualizing this three-dimensional data, and the bar chart is visualizing this guy. So it doesn't really make a lot of sense if you think about this analytically, why it's fair to compare these two. Any case, so we came up with this goofy theorem called the no free lunch theorem, which is that anytime you're given a task, either the human or the computer has to do the work. So a good visualization is usually one where the visualization already did all the pre-computation, and in that way, the human doesn't have to do them. Okay, so when we take into account of these design-specific transformations, we end up with a slightly modified version of the original InfoVis reference model. So the red stuff is the stuff that we added to sort of reveal this additional step in between that really helped us to think about the nature of what these visualizations are doing. So with this new model, what we've added are, first we added two functions, F and E. F is for data transformation and E is for visual encoding. And we added these new tables, so the three data representations. So we still have the data table D. We added this new one called prepared table, P, and then the visual abstraction is still the same as before. So more formally, we can write this as F applied over to D becomes P, and then E of P results in V. But because they're all transformations, you can actually concatenate them. So V is equal to E of F of D. Or if you really want to sort of highlight the composability of these functions, you can write it as V equals the E and F composed function over D. So here's a more concrete example of how this works, right? So we have this pipeline, D, P, and V being connected by F and E. So as an example, let's say my data set starts with a really simple one. I have 3 rows, a column called group or G, and a value called V. So imagine my design-specific transformation is about doing a group by over the count. So then what I get from my prepared table is a column with A and B, and then a count of saying there's 2 rows with A in it, 1 row with B in it. And then I can visualize this, let's say as a bar chart. So the visual abstraction looks like yet another table. So each row here represents one of the bars that you would probably end up rendering. So using this very simple example, we can make some observations. The first is that the function E is invertible. That is to say, E of P creates V, so we got that. But I can recover P given the table V. So in other words, E has an inverse. On the other hand, F is not invertible. So that is to say, I can get P from D, but I cannot get D from P, right? So F is not invertible. There's no F inverse such that F inverse of P equals D. So the observation is that because F is lossy, what this means is that D contains more information than P or V. So P or V have to be derived from D, but they cannot get back to D. So in that sense, D is strictly bigger in terms of information space than P. So what this model tells us is something like this, right? So we have these the 3 representations. And the observation is that because F and E can be lossy, we observe that D contains at least as much information as P, and P contains at least as much information as V. Sorry, typo. So we can think about this more abstractly. In other words, the space of questions that D can be used to answer is larger than or equal to that of P's. So we can write it like this, where the data query space, essentially all the queries that can use D to answer that space is at least as large as Q of P, and it's at least as large as Q of V. Sense? So yeah, and then P can be answered at least as large as V. So visually, we can also draw it like this. So the space of Q of D is at least as large as Q of P, which is large as Q of V. Okay, so there's a question. Using this diagram, why visualization? Because the idea is that we can just query the raw data QD feels more powerful because we just said that D contains more information than V. So why would I ever go to the visualization space if I know that that space is lossy? So to give you an example of why visualization is powerful, I want you to imagine a case where a scientist is trying to analyze 2 data sets that he or she has collected, and they want to investigate these 2 data sets by comparing the data distributions. So this is the query they want to write. I want to compare distribution A with distribution B. So in this particular case, this query, this compare dist A with dist B, cannot be executed because the compare function is ambiguous. What do you mean by compare? Compare is sort of ill-defined, it's underspecified. So on the other hand, a visualization is amazing because I can, in theory, execute this query by just showing you this chart. So if I give you this visualization and ask you, well, does it actually compare distribution A and B? You'd be like, yeah, okay, that feels pretty reasonable. So if we dig a little bit deeper, why can't we compute this query called compare dist A with dist B? So we said that the query cannot be executed because it is ambiguous. And what ambiguity means is that this query can represent many possible executable queries. So for instance, I can talk about this comparison as comparing the max of distribution A versus the max of distribution B, or I can talk about comparison in terms of the width of the distribution, right? If I want to be more precise, I can now even say it's not just about the comparing max of distribution 1 and 2, but I want to actually subtract them. So, so in this sense, the query compare distribution A and distribution B is ambiguous because it has a query space larger than 1. So when you write this query, it can mean many, many different things. And the argument is that when your query space is exactly 1, like this, then it becomes something that you can execute. Otherwise, if it's ill-specified, you cannot. So the claim is that, right, if we agree that this visualization is sufficiently good for answering the question of comparing distribution A with B, then the observation is that the visualization's query space has to be larger than 1. Okay, so let me be more concrete. So we started with this desired query called comparison. Sorry, I just sort of shorthanded it to CMP. So we realized that users analysis queries are often very ambiguous. And we just said that an ambiguous query can be thought of as partially specified queries. And what that means is that this one query can actually represent all of these possible things that the user might want to do. So, so that one query represents a space of all these possible queries. And the claim of this talk is that a visualization is worth 1,000 queries because I can use this one visualization to answer all of these things. So in that sense, the visualization represents a space of queries that it can be used to answer. Okay, so now we can think about a visualization as this. So this visualization represents the space of queries that it can answer. And I argue that this is an interesting formulation because we can now think about visualization in terms of queries it can answer. And this idea is very closely related to the notion of tasks, but it's a little narrower than task, which we'll come back to in a little bit. But what I like about this way of thinking is that this is a departure from the way that InfoVis thinks about it, where all these grammars and libraries are about writing down how to render the visualization in terms of its visual elements, right? So either the layout, the marks, and so on. But now we have a different way to think about this. Instead of thinking about this in terms of colors, layouts, X and Y axes, we can now just think about this in terms of the questions and the queries that the visualization can be used to answer. All right, part 3, visualizations as grammars. So earlier we just made this claim that a visualization is worth 1,000 queries, right? So why are you all of a sudden talking about context-free grammar? Well, the really nice thing about context-free grammars is that instead of writing all of these things down, this list can be gigantically long. But instead of writing this whole list, we can represent this visualization very simple CFG. So in this particular case, the comparison function stays the same, but I can now have a variable called f and a variable called t, and I have the production rules for f and t as different functions you apply and then different attributes of the distributions you care to compare. So in 1956, Noam Chomsky talks about this idea, right? So he's a guy who thought about all these computer science grammar stuff. But to describe what a grammar is that a grammar is based on a finite number of observations, and the grammar projects this to an infinite set, as the rules of the grammar can be recursively used to create an infinite set. So in this sense, the power of the grammar is that we can use this finite representation to reason about the infinite. Okay, you're still with me so far, right? So this is where sort of the big idea there is just thinking about things as spaces, thinking about things as grammars. And a few years ago, Eugene Wu, who's the collaborator on this project, Eugene and I set out to design a context-free grammar to think about data, task, and visualization. So our design goals are kind of what it says, right? So we want a unified grammar that can express all 3 aspects of visualizations. And the reason for this is that we want to be able to compare data, task, and viz in the same formalization so we can compare apples with apples with apples. We want the query or want the grammar to be able to describe ambiguous queries, as we talked about before, and be able to think about this spaces of questions and spaces of answers. And we want the grammar to allow for iterative refinement and disambiguation of these query spaces as the user can sort of add specificity and refinement over their questions. So one caveat here is that the design of this grammar, we don't particularly care about authoring. It's very similar to those examples of visualization libraries. We want to create a grammar that can help us reason, but not so much for programmability of the visualization. So, so what we turned to was this notion of hypotheses, or more specifically, scientific hypotheses. Okay, so to really think about this, you have to go back to your middle school days. You probably learned about your scientific hypotheses in your grade schools. And the idea behind this, borrowing from scientific hypotheses, is that scientific hypotheses are very well established, right? So people have written books about this. So a good scientific hypothesis is empirical, it's adequate, it is precise, and there's an explicit statement of a test. As an example of this, a statement like, the temperature goes up, volume goes up. That would be a testable scientific hypothesis that you would probably use in a scientific course. So here's an example of our conceptual grammar of hypothesis. And very similar to those principles, we want to compare two things, and we write it as a hypothesis defined as an expression followed by an operator followed by an expression followed by some optional predicates. As an example, these are valid hypothesis questions. So average price greater than 10, right? So on the left-hand side, you have an expression. On the right-hand side, you have an expression. In the middle, you have a binary operator that's greater than. So both of these examples are testable, and they will return a true false. So then, right, with that notion, you can define what the expression is, and the expression can be a constant, it can be a data attribute, it can be a function over the expression, so on, so on. For the operators, we keep it pretty simple. The operators are just binary operators. And the functions are, we'll come back to this, but just your standard summary statistics functions. So for the full grammar, it's in sort of our archive paper. You can look at it, but the purpose of this is just as an illustration to get the point across. A quick note, I'm not specifically advocating for the specifics of this grammar because it's not really important. Right? The grammar is meant to be conceptual. I wanted to illustrate how we can use a grammar to think about data, task, and visualization, but we're not actually selling it as a programming language that you need to learn tomorrow. So the other caveat is that when we talk about scientific hypotheses, these are not the same as statistical hypotheses. For statistical hypotheses, you have this whole null hypothesis, alternate hypothesis, you have to specify an alpha value, you have to have a way to interpret the results. So it's pretty complicated thinking about statistical hypotheses. But for us, we use the scientific hypothesis as a basis because it's just much easier to think about and it's much easier to evaluate. So let me give you some examples of what this grammar can specify. So as an example, you ask the question of, is the company is making money? Sorry, that's actually not a testable hypothesis. The testable hypothesis is the company is making money. And we can translate that to something like the total amount of sales is higher than cost and expenditure. So with that, you can write it as the sum of sales greater than the sum of cost and the sum of expenditure. Going back to that middle school science class, if temperature goes up, volume goes up. We can rewrite that as there's a positive correlation between temperature and volume. So now we have correlation of temperature and volume greater than 0.9. We can ask questions like the horsepowers of cars since 2000 follow a normal distribution. So we can write that as applying the KS normal test over the attribute horsepower. And here we introduce the predicate where we specify the year has to be greater than 2000. And the KS normal test in this case uses alpha equals 0.05. So there are other examples of how we can do this. So we talked about how to use this grammar to pose questions for the VAST 2017 mini challenge. Interested? So the idea here is that with this conceptual grammar, we can now use it to reason about concepts related to data visualization and task. So here's an example. Imagine that I give you a very simple data set with two columns, just cost and price. So here's the grammar. Now, I want you to look at this for a second, because the argument here, you have to use a little bit of your computer science theory of computation training. But the claim is that this grammar, right, this thing I just wrote, describes all possible hypotheses you can ask of this two-column data set. Anything that you want to ask about this two-column data set, as long as it fits this expression or this format of expression, operator expression, it is described in this grammar. So this is going back to the power of a CFG, which is that we have a very concise, finite representation, but through this representation, we can reason about the infinite, all the possible permutations of comparing values in these two columns. So of course, we have to make some assumptions here, which is that we have a finite list of functions and we have a finite list of operators. So in other words, we have to pre-register what the functions are. you have to pre-register what the operators are for this to work. And before you ask the question of like, oh, how complicated are all the list of possible functions? Well, in SQL, standard databases, your aggregate functions are extremely short. So it's just average, count, first, min, max, sum, that kind of stuff. Back to this point, right? So if I give you this grammar, the idea is that you can use this grammar to enumerate all possible statements that are acceptable by this grammar. So what this allows us to do is to think about this in terms of a space or a set. So here's a definition. The set of all parsable statements given a grammar spans a hypothesis space, which we call H. We're further going to say that the size of this hypothesis space is the number of parsable statements. We're going to call it vertical bars H. So what that means is we can imagine a mathematical space of all possible hypotheses in the world H. And when you have a given data set D, the data hypothesis space is then thought of as a subspace of H, like that. So, right, so this is a pretty cool way to think about things because now, given a data set with some assumptions, we can enumerate all possible hypotheses or what you can call analysis questions that the data set can be used to answer. So in a way, what we're doing is transforming the representation from sort of a typical data format into this grammar format, thinking about the data in terms of the questions as opposed to its raw values. Right. So a couple of caveats. The grammar does not allow for feature engineering or data transforms. We can't do group bys in this case. We can't add new columns. There's some other additional considerations, like we didn't talk about the predicates and filtering with the predicates. So these are sort of omitted without the loss of general. So it turns out that we can play the exact same trick, but instead of thinking about the grammar to represent a data set, we can now think about the grammar to represent questions that an analyst might have. So in this case, the red things that I just added represents potential attributes that an analyst might care about, as well as new kinds of functions, right? So for instance, analysts might want to know not just the cost and the price or whatever, but want to know how much the cost might correlate the year and how it might correlate with interest rate and so on. And the important thing here to note is that the analyst questions are not actually tied to any particular data set, but you can still write it down in this sort of formal way. So again, now we spend a grammar which represents a space as well. So we can go back to our big diagram to add an analyst hypothesis space, H of A, which looks like this. So just with these two spaces, we can start to think about interesting relationships. If I have a grammar that represents all the possible questions that a data set can be used to answer, and I have a space of all the questions that the analyst cares about, but the two sets don't overlap in any way, that means that my data set is inappropriate for answering the analyst questions. If they overlap like this, you can say that they do overlap, but the analyst question is bigger than what the data can answer. There's insufficient data for answering all the questions. And then the reverse of that, I'm not 100% sure what that means, but too much data, the analysis is I'm not sure. But the point is now you can start to reason about the relationship between spaces. Fun fact. So when you think about the intersection of spaces, because each of the spaces represents a grammar, so the intersection of HD and H of A can be described as yet another grammar. So essentially just computing the intersection between two context-free grammars. So the last thing I will say is the notion of visualization hypothesis space. And now I will tell you that this is really wacky and really wonky. It doesn't really fully work. But just as sort of a point of illustration, I can think about it as 3-bar bar chart. And I can write down the hypotheses, which are bar 1 is greater than bar 2 is greater than bar 3. And I can talk about some sort of functional fit over the 3 bars being something or other. But the point here is that we can now try to think about what a visualization can be used to answer in a similar way. So that allows us to add the last circle, which is the hypothesis space given a visualization H of V. Okay, so altogether, there's lots of these possible relationships you can think about. I'll omit that for now. If you're interested, come talk to me. The interesting thing, of course, is to think about what can we do with this sort of representation. So the problem is we have some ideas, but we're not sure what to do. So first of all, it's a great sort of theoretical way to think about visualization and analysis, but we're still thinking about really what can you do with it. And one of the reasons for that is because we understand that this grammar is just a proof of concept. It's not really operationalizable yet. And because our purpose is really just to illustrate how this grammar-based approach can think and change the way we think about visual analytics at large. So if you have ideas about how this sort of grammar-based representation can lead to sort of the development of a language tool or something of that sort, I'd love to talk to you. You'll be great to chat. But I threw out some basic ideas here. Some of these are sort of more interesting to me personally than others, but just as an example. So typically we think about visualization recommendation based on data types. So Tableau Show Me, Dominic's Draco, they're all kind of the same things, which is you give it a data set, and then the system says, oh, based on the data attribute types, you get a bar chart. Based on data attribute types, you get a scatter plot, whatever. So the idea now is if we have this grammar, we can consider recommendation of visualizations based on the visualizations that can best answer somebody's questions. So as an example, here's the grammar representing an analyst hypothesis. If a visualization V1 can answer that versus visualization V2, we can answer that, we can probably pretty confidently say that V2 is a better viz than V1 for this task. And it also leads to new questions. So if I have a visualization that's so much bigger, which one do you use? Don't know, but it's a different way for us to think about it. I'm going to fly by this notion of hypothesis-driven analysis, just noting that the way we typically think about data analysis in the viz world follows a data-first approach, right? So usually we think about somebody giving you data, do some sort of exploratory analysis to get some ideas. Based on the ideas, you can now propose new questions, maybe collect new data, do transformations, and that leads to more of the analysis and the explorations you can do. But whatever the case, the point is that the current workflow of basically all data science starts here. But in the scientific community, we're asked to pose hypotheses first. So in the science world, it's very important that, in fact, it's actually the scientific method. Right? The scientific method says you can't just collect data and run statistics. You have to pose hypotheses first. So in that world, you start here. You do not start with data. You start with a human asking questions, and then you collect data, and then you test them, and so on. So all of that is because you want to avoid the notion of parking, p-hacking, and all that stuff, right? So this is an idea that people have talked about in the Viz community, which is, can we get out of this data-first approach to think about hypothesis-first way of doing data analysis? Anyways, so with a grammar like this, we might be able to get to realizing a hypothesis-driven analysis approach, but that's sort of future work. The last thing is to think about evaluation. So I think as a community, we still struggle with evaluations, usually just measuring time and error. But now, again, right, with this formalization, we can start to think about things in terms of the hypothesis space and the space coverages and so on. So for instance, how much of a data hypothesis space does a Viz tool cover? How much does a Viz tool support the user in changing their hypothesis space, the analyst hypothesis space, H of A, and so on, so on, so So this is an idea that we started to think about. We had a short paper at Euroviz a couple of years ago that starts to explore this notion of evaluation not based on time and accuracy, but based on the sense of space coverages in this sense. Okay, so that brings me to the end. So as a summary, I would like to advocate this idea that thinking about visualizations as queries, languages, and grammars can be a valuable path forward to building a foundation for the visual analytics community. So the two systems that I mentioned were HomeFinder and this NeuroCubes thing that we built to illustrate that a lot of these systems are in fact just wrappers around queries. I illustrated about data, prepared data, and visualization can be thought of as query spaces. And I suggested that there's a reason why we can think about visualization as this powerful mechanism, which is that a visualization represents the ability to answer 1,000 queries, right? A really large space of queries. So we show that using the design-specific transformation idea. And lastly, I sort of suggest that these query spaces can be expressed as a context-free grammar. And once we start thinking about visualization in this way, we might be able to start to describe data, task, and visualization, because again, context-free grammars are so powerful as a very compact representation, very sort of finite, but allows us to really think about the nearly infinite spaces of queries, questions, and so on and so on. Okay, so with that, thank you guys so much. Really appreciate your time. Happy to take questions.
Yeah, we time for question. Anybody? Anybody? Yeah, Ming first. Yeah, yes. Hiding there. Yeah, turn on the mic. There's a button. You need to turn it on. You got it? You see? No, I guess because let me come, because we need to let the people online hear it.
Oh, this one works.
Okay.
Yeah, this one works. I follow this one. Great talk, Remco, and excellent. I follow everything you said. So I was wondering, and when you talk about the hypothesis or query, what some of those queries human simply can't answer easily, have to use algorithm or machine learning or AI.
Wow. Yeah, that's a great question. I had not thought about that before, and I want to mention that I put your name into my slides, not because I knew you were here to butter you up. I really thought that you work on sort of thinking about visualization as sort of information theoretic reduction and so on as very inspiring. So still use our work as sort of a way to think about this type of stuff, right? So but thank you, Min. I appreciate you being here. So in terms of what are the things you need to do with machine learning and AI, I think that
I think we can talk after. I'm going to suggest
Yeah.
a modification to your thesis. Say the visualization is worth 1,000 queries. I agree totally.
okay.
I would add on a visual analytics is worth 1 billion queries.
Yeah, okay, but I have a reason. I think there's a way to talk about that, but it's the idea that allowing for interaction opens up the query space in such a exponential way that it makes it such that from a human user standpoint, you just don't have the time and energy to fully explore that entire space. You just don't have time. Space is too large.
Agree with you absolutely. We could even change it that the visualization was 1,000 and the interactive visualization was 1,000,000 and visual analytics was the billion.
Sold. Okay. All right. Thanks, man. Appreciate it.
Hello, thank you for the great talk. This is Hyun from Seoul National University. So throughout the talk, it was really insightful, and I really appreciate your talk about all these things that you have developed. So my question is about actually analysts. So what I recently found throughout my research and also all the folks in this visualization community is that analysts also makes mistakes. So I'm really curious about how these foundational frameworks can be inform these analysts, like not only the visualization researchers, but there's like a tremendous of analysts throughout the world, like not in this field, but also in other fields like biology, business, etc. So how can your grammar and this theoretical foundational framework can be used to inform them, to guide them to do more reliable or maybe efficient visual analytics?
That's a great question. So one of the things we did not get into is, right? So if you think about, I'm going to use a home finder example because it's so simple. So if you think about this home finder example, you can think about sort of the provenance of the user's actions as essentially is just a recording of how this grammar or how this query changes over time, right? So the first thing, not exactly to your question, but the idea is that the analyst can change your minds. They can change your analysis trajectories. But if you represent your visualization system in this formal way, then all the process is documentable. All of it is sort of recorded in this formal way as well. So that's the first answer. The second one, I guess, is that I think for a lot of domain users, one of the biggest challenge like I've encountered is that the initial, the initial data set is so big that it's really hard to enumerate what's actually interesting. So you use the analyst as a way to essentially filter that space into things that they actually care about. So the way that we're thinking about this is that the data hypothesis space never changes. Once the data is fixed, that space is fixed. But the analyst hypothesis space is very mutable. It's something that can sort of morph and change and define, if you will. And here's sort of the kicker, which I didn't have the time to go into, but well, you can start with a very large hypothesis space, meaning that the space includes lots and lots of questions. But as the user gains insight, what they're really doing is they're adding specificity to that grammar. In other words, they're shrinking the hypothesis space. And as you sort of add the predicates, add particularities or specificities, shrink. Now, in my experience, it never shrinks to just one single query. Ever. I've never experienced that. But get to a point where it's small enough, now the user can use visualizations and tools to be able to examine that whole space. So I think the role of visual analytics systems is not to answer questions per se, but I think the role of visual analytics systems is to... That's how I think about it. Happy to chat afterwards. I don't know if you agree with that, but love to hear your thoughts as well. Hi, Bettina.
Yeah.
I really like your formalizations. I mean, as a classical algorithms researcher, I love all of these things. But I want to kind of follow up a little bit with what Ming said. The answers, how do you compute them? So you were speaking about AI and ML. And yeah, well, the answers are just not as formal as the queries you put in. I mean, you just do not get crisp, clear answers from such a system. Whereas, I mean, you do get them from a classic algorithmic system or from a classic database system. And so I feel there needs to be extra reasoning here about the quality of the computations you do in the background, or like extra communication back, right? If you have super crisp query in,
yeah,
and then you get something out that is not that good because you cannot trust it fully.
Yeah, I mean, I have to be honest, like this AI stuff sort of doesn't fit all these things, right? Like the idea that,
Exactly.
it's a great point. Like if somehow you execute a query and the results sort of stochastic, I think all this stuff is toast. I don't know how to think about it. But I think that, right, so coming back to this though, is that if we don't think about this in terms of like accuracy of the computations, but think about this in terms of the accuracy of the visualization, then it's again a different set of argument, right? So I think if I ask everybody in the room all the possible questions that this viz can answer, we're probably also going to get slightly different answers across the board. It has to do with visual literacy, it has to do with blah, 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 whatever, right? So even there, I don't think that this formalism is quite complete yet because we can't really nail down this. But the whole point of this talk is to be provocative and say, this might be a way forward. Somebody please prove me wrong. Yeah. Happy to chat afterwards as well.
Yeah, we can still. Oh, yeah, please. Hey.
I may.
Can you hear me? Oh, okay. So yeah, so I was really curious because the sort of order diagram towards the very end sort of appear to have this information that some of those spaces are sort of finite. Some they all appear to be finite, but it does not seem to be. Seems like there is this argument that if you give the data the space of hypothesis space of the data seems to be countable to some degree.
Yeah.
Okay, there's a differentiation between countability versus whether something is infinite or not.
Yeah.
So I was wondering if you can comment a little bit over those, because I somehow feel that the hypothesis space of analysis may be infinite.
Yeah.
So how do those things fit together if you think about countability and infinite spaces?
Yeah, so you're the mathematician, so I'll defer to you on this. But you're 100% right that all of these can be trivially infinite, right? So I can have this being a statement, average price greater than 10. I can have average price greater than 10.01, 10.001, 10.0001, 10.000. So there's literally an infinite number of statements given any hypothesis group. Trivially so. So I think to make it sort of operationalizable, you do have to bound it a little bit. Either you can just say precision. I mean, we're computer science, really good at like discretizing the infinite. I feel like. Maybe, possibly. Okay, but like I think, right, so the obvious thing is you can cut the level of recursion, right? Or you can essentially specify the number of decimals you're allowed. And whatever the case, you can sort of essentially choose the right bin sizes. That makes something that's sort of infinitely infinite into something that's more manageable, maybe still close to infinity, but like in a way that's more manageable and useful. Because I think the question about greater than 10.0001 versus 10.00001 is just interesting. But you're right. I mean, sort of blur that line a little bit without being super precise.
Ivan?
To this point, I think I would argue that, okay, you can add everything, but I mean, first of all, we have discrete precision, which, in my opinion, would make it finite, but so it definitely is not infinite.
Yeah.
Because even if you can, if we would have infinite precision, whatever you type in would be somehow mappable to rational numbers which are countable. So there is a bijection to the natural numbers. So I think it would
What he said.
It would not be infinite. It would be probably finite at the most countable, I think, if I'm using the right English terms, because I learned them in a different language. But
Countably infinite.
so first is finite. This is like and countable is like many, but still you can have a bijection. And then the second thing, which I think your talk was very thought-provoking in many aspects.
Thank you.
And this neural network which you presented, I mean, yes, we have a great reduction. And the explanation could be in some sense also simple. Why? Because we simply have the conditional expectation or an average of a regression function. So you take away all the distribution and you just have your, the weights and biases will be giving you the regression function if you are using like maximum likelihood estimation or maximum a posteriori. And if you have maybe a Bayesian, then you might have additional statistic to the mean, kind of for each data point which this neural network is giving you. So I think it's just it could be quantified by the amount of capacity you give it, the adequate interpolation, if you like, will be achieved from that. But you will throw away all the non-trends, all the distribution represented by those samples. And in that regard, you might lose that you want to buy a cheap house and you can never get to that because you have thrown that away.
Yeah. I think this is a conversation best when Min's around. But I do agree that right, when we think about this reduction in this way, probably a lot of the really fine level information is thrown out, first of all. But also, and Min, please, rescue me if I'm saying this wrong. But in a way, you might even be able to think about the visualization as a filtering mechanism, because the viz as the viewpoint into the data is extremely restrictive. So it's not all the possible things you can do to the data, but it's all the possible things you can do to the data through this particular visual representation. So, and by the way, so can sort of become deflated a little bit about our community, which is that what we're actually showing to the user, similar to Ben Schneiderman's overview first type of thing, it's a really potentially very biasing and potentially very limiting way into thinking about what the data really represents. Standing up.
I think I probably using the analogy of a Google map. And if you think of the Google map is an example of the hypothesis space, which the Remco is talking about, then globally, anyone using Google Map, all collecting possible use together, that would be all the possible use as the Remco's one. But what Remco tried to say is when you, individual of us, when we zoom into one particular city, and our hypothesis space is tiny compared to the potential Google Maps hypothesis space.
Thank you.
So we have one last question, then we'll coffee break.
Thank you.
Awesome.
Thank you for the great talk. And
you.
I'm Ken Wakita from Science Tokyo. The previous discussion was quite interesting. And I wanted to add one aspect from the human-computer interaction view. So I understood that you provided many spaces which are potentially infinite. However, due to human comprehensivity of visuals and query and everything, probably we are not that interested in a huge big query or too complicated visualization. In the latter part of your talk, you suggested a constructive way to explore the space of the I'm still
No, it's good.
But in that, and it's reasonable to cut according to the level and the width of the recursion, but also maybe we can consider about what kind of query or what kind of design we can go into. Maybe that differs from person to person. And so do you have some suggestion in that direction?
I think that's a great question. And maybe we can talk more about this offline. But the general idea that, right? So it's a great question. Probably the chat offline. Okay, so here's the question: is to render this visualization, you use this query. That's true. But if you run this query, it doesn't necessarily mean that this is the visualization for it. right? So there's sort of a mismatch in between. So right, this way is true, that way is not. So I can use the exact same query. I can design infinite number of visualizations to look at the results. And I think that's sort of the design spaces. That's sort of the interesting part, right? But one of my sort of secret hope for the VA community is instead of just talking about, oh, hey, this is the amazing tool I built, we can start to expose the underlying mechanisms in the queries that's written. Because at that level, we might be able to say, oh, hey, here's 2 visualizations all about home finders, but I can compare them, first of all, at the analytical level. What are the questions they're trying to ask? And distinguish them. And then the second question is, what's your visual representation? What's your choice of the representation? I can sort of compare and contrast visualizations.
Let's thank Remco for his insightful talk.
Thank you, guys. Happy to chat offline.
I think we're actually going to go fast forward instead of coffee break.